Hello, calculus fans! So in one variable calculus, we found out that it's really pretty hard to evaluate single integrals directly from the definition. That is, the limit definition, where we evaluate a limit of a Riemann sum. What we really ended up doing was we introduced the fundamental theorem of calculus. That gives us a much simpler method. If we tried to evaluate double integrals from the definition, that's even more difficult. What we're going to do now is see how we can express a double integral as what's known as an iterated integral. We'll evaluate two single integrals, and of course we'll use the fundamental theorem of calculus on both. So let's suppose that f is a function of two variables that is integrable on the rectangle R, AB cross CD. Usually that happens because the function in question is continuous. We're going to use the notation, the integral from c to d of f of xy dy, to mean that we're going to keep x fixed. That is, we'll pretend that x is just a number, and then f of xy will be integrated with respect to y, from y equals c to y equals d. This procedure is known as partial integration with respect to y. You should notice the obvious similarity to partial differentiation. After we perform a partial integration, we get something that is a number that depends on the value of x. So this thing defines a function of x. We could, for instance, say that a of x is equal to the integral from c to d of f of xy dy. If we now integrate the function a with respect to x from a to b, we'll get this. That integral on the right-hand side is called an iterated integral. Now we often will just omit the brackets and we'll write this. In a similar way, we can write down an iterated integral going the other way. That means we first integrate with respect to x while pretending that y is a constant, and then we integrate the resulting function of y with respect to y from c to d. Notice that in both cases, we're working from the inside out, so it's the innermost integral that we're doing first. Let's do an example. Let's compute this double integral by using an iterated integral, and we'll do it in both orders. So if we integrate in the order of dy dx, that means we're integrating with respect to y first and then x. This is the iterated integral that we need to evaluate. In the other order, it's going to look like this. The integrand changes the same, but now we're doing dx dy. Also notice that these limits of integration go with x because they are the outermost. These limits of integration go with y, they are the innermost. Everything is swapped in the second integral. Let's evaluate that first integral. So the first step is to evaluate the inside integral with respect to y. So if we write down an antiderivative of 4x squared minus 9x squared y squared with respect to y, we'll get 4x cubed y minus 3x squared y cubed. And that gets evaluated from 1 to 2. Notice here that we're using the fundamental theorem of calculus. That inside integral, when we plug in the 1 and the 2 and subtract, we end up with the integral from 0 to 1 of 4x cubed minus 21x squared dx. At this point, now we have a dx integral to evaluate. And if we work all that out, we get a negative 6. Notice that because it's a negative number, there's no way that this could represent a volume. If we're looking for an interpretation of this integral, we'll have to wait. We'll wind up with some interpretations where the integrand is not always positive and the result is not always positive. Let's now evaluate the second integral. This time we evaluate the inside integral first. That's a dx integral. Once we've evaluated the inside integral, then we're left with a dy integral. And we end up with the same thing, a negative 6. And this is no coincidence. We're going to talk about this in a moment here. that it really doesn't matter which way we evaluate the integral, we're always going to get the same result. That means we should always evaluate the integral in the most convenient way. And later on, we're going to see some integrals where integrating in one way is easy, integrating in another way is hard or impossible. Okay, that's all for now.